Okay, so this is part D of homework 2. So we're going to be implementing an iterative Radford-Rice calculation to our isopropanol water system. And we're going to take these guesses for the vapor fraction and liquid composition and see if we can obtain our dew and bubble pressure calculations. And we're just going to be using the code that we've built in part C. So this is also part D right here. And in terms of guesses on how we're going to start this, these are our start for the guesses on using these. So we've already made that, so we don't have to do anything with there. We'll just have to refer to them. But we will start with our NRTL dew temperature, where we will have our Y and P value. And then we will go ahead and define our T initial and X initial, which is just our dew temperature in respect to this would be respect to Y and P, and then we'll have our V initial value. This will be NP.P underscore T initial and X initial. Then we'll also have to obviously define our fruit. So we can find our roots, which this we will just return with. So before we start with return, we're going to define our temperature, which is just our initial V, and then X, which is all the other values after that initial value. And then we can go ahead and return with P.P underscore, and we're going to use a slightly similar equation, which is right. Oh, no, not that one. No, it is. Yep. Just going to take that and chuck it into here for the sake of time. And this is going to be minus Y, and then you'll have sum of X minus 1. And then we can write our res equation, which has been a minute since we've used that, underscore root, and we'll have our fruit and our V initial value dot X, and we're just going to return our initial res value with our all the other values right there. Let's just check if that works. Oh, we have to run off. Yep, that works perfect. So now we're going to get into using our Radford-Rice, but first we're going to define our flash and use ZPT, have our niter set as 100, and our tolerance is 1e to the negative 6th, and then we're going to have our bubble pressure, our dew pressure, or it's going to actually be X dew underscore NRTL underscore dew pressure with respect to Z and T, and then we'll have our dew pressure with bubble Y, and we're going to make that with respect to bubble P with respect to Z and T. And then we want to put in a few if statements, and we used this before. If our pressure is greater than our bubble pressure, then we're going to return with all liquid. And if our pressure is less than our due pressure, then we will return with all vapor. Next, we're going to go ahead and define our phi, which we did in, I believe, part B. I think so. So this is going to be minus BP divided by our dP minus BP. Then we'll also define our x, which is phi times our x due minus 1, or minus z plus r z. And then for I in range of niter, we're going to define our k value, which is what we have used before, which is np dot p, or p dot nrtl underscore gamma in terms of x and t times our x times p dot pvap of t divided by p. Now we're going to define our fruit, which actually I think this just goes straight into the for statement. I might have to double check on that one, but we're going to go ahead and make our define fruit, which can return with jmp.sum, and this is where our Radford-Rice equation comes in from, I believe, part A or B. And then we're going to have our 1 plus phi times k minus phi. Yep. And then we're going to define our fruit prime, which is jax dot grad in terms of fruit, and then we're going to define our phi as sp dot optimize dot root underscore scalar fruit, where x initial is our phi, and then yep, did get that right. And then our x new is going to be essentially our Radford-Rice without the k minus 1 in the top. Now 1 plus phi times k minus phi. And then we're going to have if np dot linealg dot norm, where x minus x new is less than tolerance, then x equals x new, and then we'll break x will equal x new, and then y equals k times x and then we will return finally with phi, x, and y, and then go ahead and run all, see if it works. Yep, no errors. So now finally we can go ahead and call upon our NRTL flash PT function and build an array. And in the problem statement, it states that our feed composition of 25 mole% of isopropanol at 1 bar at 360 Kelvin. So we're going to go ahead and state that our composition is 25% isopropanol and then 75% water. And then since we use pascals, we're going to have 1 times 10 to the 5th at, is it 360? Yep, 360 Kelvin. And we should just where is X new break? Yeah, where is that? Be right back. Okay, so I genuinely don't know what the issue was. I didn't change anything. I just rewrote it and exactly the same, and it kind of just worked. So, yeah, I mean, I don't know. So we did get our values. So this is our isopropanol. Shows that 0.05 will say it percent is liquid, 95% is vapor. With water, it's 40% and 60%. So we've successfully used our Rackford Rice calculation to calculate the VLE of the isopropanol water system, utilizing our guesses and vapor fraction and liquid composition um, by using the dew and bubble pressure calculations. So there we go.